I am Rishi Raghavanshi. Welcome back to my YouTube channel. In this video, we discuss the topic dimension reduction. Let's start. Dimension reduction. Dimension reduction tackling multicollinearity and principal components of analysis. This video dives into the world of dimension reduction, especially addressing multicollinearity and its solution, principal components analysis (PCA). We will cover identification, handling, and application of these concepts in Python. First, we have to identify multicollinearity in Python. There are two types of multicollinearity in Python: correlation matrix and variance inflation factor (VIF). First, correlation matrix. A correlation matrix usually Correlation matrix. A correlation matrix visually display the relationship between features high absolute value close to 1 or minus 1 indicate strong correlation suggesting multicollinearity. Now, variance inflation factor BIF. BIF measure how much the variance of a regression coefficient is inflated due to collinearity. A BIF greater than 10 suggests high multicollinearity. Next, handling multicollinearity with feature selection. In this, we have backward elimination, forward selection, and feature importance. Backward elimination. Start with all features and remove one at a time based on statistical significance or BIF until an expectable level of collinearity is achieved. Next, we have forward selection. Start with no features and add one at a time, selecting the features that most improves model performance until an expected level of collinearity is achieved. Next, we have feature importance. In feature importance, using algorithms like random forest, evaluate the importance of features and select the most relevant ones to reduce multi-collinearity. Latency reduction in Python can be achieved using several techniques that aim to reduce the number of input variable while retaining the essential information. This is useful in machine learning, especially when dealing with high dimensional data to improve performance, speed of algorithm, and avoid overfitting. Here are a few popular methods for dimensional reduction in Python. First, PCA, Principal Component Analysis, is a linear dimensionality reduction technique that performs the data into a new coordinate system based on the variance of the data. The first principal component captures the maximum variance, the second captures the second highest variance, so on. Using PCA in Python, we have to write this code: import numpy as np example data. Let's say x user data with shape and feature. Initializing PCA method and reduce the dimension. PCA and components reduce to two dimension. To print, we use original shape, or to get the new shape, we use reduce shape hex reduce dot shape. Now, PCA is great for unsupervised linear data. TNF is often used for visualization of high dimensional data in 2D and 3D. LDA is useful when you have labeled data and want to reduce dimension while preserving class severability. Autoencoders are deep learning based method that can handle more complex nonlinear relationship. Select best Select k best is a simple feature selection technique based on statistical test. Each method has its own use depending on the type of data, whether it's linear or non-linear or supervised or unsupervised. What's our goal? It's for dimensional reduction. We have introduction to PCA. Data transformation. PCA transform correlated features into uncorrelated PCS principal components, reducing dimensionality while preserving most of the original data variance. Next, linear combination. In linear combination, PCs are linear combination of original features where each PC capture a specific direction of maximum variance in the data. Next, dimension reduction. In dimension reduction, while selecting a subset of PCs, we can reduce the dimensionality of the data set, making it easier to analyze and model. Now, applying PCC in Python. Import libraries. Import necessary libraries like sklearn for PC implementation. Standardize your data to ensure all features have a mean of 0 and standard deviation of 1. Fit PCA. Fit the PCA model to your standardized data to obtain the principal component. Next, interpreting PCA result and explain variance ratio. Explain variance ratio. Each PC explain a certain proportion of the total variance in the data. The explained variance ratio tell us how much variance is explained by each PC. Now, screen plot. Screen plot visually display the explained variance ratio of each PC. The elbow in the plot indicates the point beyond which adding more PCs contributes little additional information. Next, selecting the optimal number of principal component. In this, we have three types: cumulative explained variance, screen plot, and cross validation. First, examine the cumulative explained variance of PCs. Choose the number of PCs that capture a sufficient proportion of the total variance, like 80, 70, 90%. Screen plot. Identify the elbow in the screen plot where the explained variance ratio starts to plateau. The number of PCs before the elbow is often considered optimal. Now, cross validation. Use cross validation technique to assess the performance of model with different number of PCs and choose the numbers that yields the best performance. Now, benefits of dimension reduction: improved model performance, reduce complexity, simplify data. Simplified data with fewer dimensions can lead to simpler and more interpreted models. Improved efficiency: less complex models can train faster and require fewer computational resources. Enhanced generalizability: reduced dimensionality can prevent overfitting, leading to models that generalize better to unseen data. Applying PC in MLM, machine learning model. First, we use featuring extraction using the fitted PCA model to transform the original features into principal component. Next, model training. In model training, train our chosen machine learning model using the transformed data PCs has input. Next, performance evaluation. In performance evaluation, evaluate the performance of the model on a test data set to see if dimension reduction has improved accuracy or efficiency. Now, unleashing the power of dimension reduction. First, tackle multicolority. Use techniques like correlation matrix, VIF, and feature selection. Next, apply PC. Transform data, select optimal components, interpret result. Next, improve models. Gain benefits like reduced complexity, enhanced efficiency, and better generalizability. Stay tuned for upcoming videos. Thank you.